The following program has been made possible by a grant from Champion International Corporation. For 7 years, a great drought has afflicted Africa. Where crops once ripened, fields have turned to dust. Millions of people retreated before the advancing desert. But in 1974, an eye in space observed the life-giving rain clouds once again spilling deeper into Africa. The machine that makes the world's weather keeps changing gear. The weather satellite shows a planet that grieves for its lost harvests, while the price of food keeps going up. Good evening. Are the better rains of Africa a sign of hope, or just a deceptive pause in the southward march of the Sahara Desert? At any rate, the Earth's climate is varying in little ways that may spell big trouble for all of us. The rains have been desperately late in coming to the parched farms of India, while nearby Bangladesh was awash with fatal floods. What's happening to the monsoon that feeds half of Asia? Again and again, the newspapers and television have been reporting weather disasters. In 1974, the Midwest suffered its worst drought since the 1930s, and deadly tornadoes were on the rampage. But we'll find, strange to say, that the Japanese actually welcome the great typhoons that bring floods to their country. And we'll examine why so many places have been having cool and dismal summers. The weather machine's an all-embracing system of air and water and ice, three fluids that work together between the tropics and the poles and govern all our lives. In this program, we'll visit the frontiers of present knowledge about our ever-changing weather. We'll go, for instance, to the tropical Atlantic, where 40 research ships from 10 nations have spent the summer. Because it's sunny or wet, warm or cold in North America today, according to what was happening in the tropical air last week, in the oceans 2 weeks ago, and in the polar ice many centuries ago. Here's where we begin, in the barefaced ice of Greenland. In the great ice sheet that buries Greenland, the snowfalls of 1,000 centuries are piled up to 2 miles in thickness. The air is thin here, and remote from anywhere in the vastness of the ice, men have planted a frail encampment. They're drilling for ancient ice deep under the surface. The deeper, the older. An earlier drilling at another site went right through to the bottom of the ice. This time, they're going down just 1/4 of a mile, through 1,400 years of compressed snow. Nowadays, men can tell the climate of past centuries from a piece of ice. That's why they've come here, to a ridge of the ice sheet at a map reference known as CRET. In 1974, polar engineers of the U.S. Army and scientists from Denmark and Switzerland have been sharing the work around the clock under the unsleeping sun of summer. In this season's drilling, the oldest ice recovered is more than 14 centuries old. The snow that made it fell shortly before the birth of the Prophet Muhammad. As one team of scientists takes over from another, some of the ice samples go to Denmark. But where are the snows of yesteryear, a poet wanted to know? They're here, in cold storage at Copenhagen University. The Pope was grumbling that the sea ice had stopped any bishop from visiting Greenland for 90 years when these snows settled on the ice sheet in 1492. In fact, his Norse congregations had perished long before. But how can you tell of changes in the climate just from the ice? One piece looks very much like another, especially when they're melted. But this laboratory's business is to weigh the atoms of oxygen that the ice contains. First, the melted ice swaps oxygen atoms with carbon dioxide gas. When the gas has a fair sample of the oxygen atoms from the Greenland ice, a powerful magnet sorts them according to weight. The amount of the rare, heavy sort of oxygen is what matters. The heavy oxygen varies from layer to layer, century to century. More of it found its way into the Greenland snow whenever the world was warm. In very cold times, the heavy oxygen was scarce. So, the Danish climate hunters make thousands of measurements from different drillings while they unravel the age and history of each piece of ice. As the computer puts together the results from consecutive samples, the younger ice reveals even the changing seasons year by year. The heavy oxygen rose to a peak each summer. Then it fell away again in the winter. It's a great help for accurate dating. For Willy Dansgaard, his laboratory is a time machine. It recaptures the climates that our remote ancestors knew. In Napoleon's time, it was a good deal colder than the 20th century. It was colder, too, in America's early colonial days. And in William Shakespeare's winters, milk came frozen home in pail. The Little Ice Age, it was called. But the Vikings made their forays when northern lands were much warmer. The cold came and went. The Roman Empire flourished during another warm spell. And so, long before it, did the Egypt of Tutankhamun. But if we go further into the Greenland ice, more than 10,000 years, we're deep into a real ice age. Our ancestors who made this goddess 30,000 years ago faced the big freeze that began long before. The Copenhagen physicists think they see, during the last 8 centuries, 2 separate rhythms of warmth and cold. Add them together, and the match is quite good. It's cooling now. If those rhythms are real, you can make a forecast. Chilly for 100 years, then warmer, perhaps. But 200 years hence, cold again. It's only a half-joking forecast, yet it tells of an inconstant climate that could alter all our lives. Just how reliably do the Greenland snows register the changing climate? Are the rhythms real? The drillers go again and again for checks on the bleak forecast. Far below, an unseen land sags darkly under its burden of ice. And around the edges of the ice sheet, the glaciers, sluggish rivers of ice, lick the landscape with their frozen tongues. Nature's ice dwarfs us and outstrips our own efforts to alter the planet where we live. The ice can seize or release huge areas of land and affect the climate even in much warmer places. Besides the risk of somewhat cooler weather in the decades ahead, there's the ever-present threat of a big freeze. Will a new ice age grab our lands and erase our northern cities? It's buried Manhattan Island before, when great glaciers half a mile thick filled the valley of New York's Hudson River. That's what an ice age is all about. George Kukla is from Czechoslovakia, where he discovered signs that ice ages are far more frequent than most experts have supposed. Today, he continues his work near New York City as an exile. For him, the next ice age is not at all remote.
Well, almost all of us have been pretty sure that there are only 4 ice ages, separated by relatively long warm intervals. But now we know that they were 20 in the last 2 million years. And the warm periods are much shorter than we believed originally. They are something around 10,000 years long. And I'm sorry to say that the one we are living in now has just passed its 10,000 years birthday. What of course means that the ice age is due now any time.
The threat of ice is another of our themes this evening. Not only New York, but most of North America was buried during previous ice ages. This could be a postcard of Chicago when that happened. And here's how Los Angeles would have looked in an ice age. Right now, we're living through a period of cooling. But before you sell your house and head for sunnier climes, scientists think it's much less likely to be the start of the big freeze than a return towards those cooler conditions our forefathers knew. A little ice age. Of course, that's bad enough, particularly in our era of expensive fuel and scarce food. Hindsight now tells us that in the 1940s, the world was warmer than at any time for almost 1,000 years. Many of us are old enough to remember those sweltering summers. But since then, our northern countries have become cooler. The armadillos of the Midwest have shifted south, apparently on account of the cold, while the snow geese of the Arctic have found their breeding grounds obliterated by snow that lies all summer. For European farmers, the growing season has become shorter. Another change is that there's too much rainfall sometimes in parts of North America that were persistently dry in the 1930s. All of these occurrences are linked because the weather machine works as one system. Its chief job is to hold back that polar cold by spreading the heat of the tropics. The air is the first of its working fluids. The whirling movements you see in these satellite pictures are produced by the spinning of the Earth, but the sun's rays drive the whole machine. They're absorbed by the water and the land, which then heat the air from below. High up, the air is cold. Among the main features of the weather machine are the great clusters of clouds in the tropics. Yet they went almost unrecognized until satellite pictures showed them strung across the oceans. The clouds are signs that the air is rising. The tropical oceans are the Earth's chief boilers that keep us all warm. And the cloud clusters pump billions of tons of air sky high. It starts off towards the poles, but it soon comes down. Sinking air makes no clouds, no rain. So this is the zone of deserts. Then the air flows back through the tropics at the surface as the trade winds. Meanwhile, cold air from the Arctic is seeping southwards, as if trying to chill the world. In between, the contrast between warm tropical air and cold polar air powers a jet stream. It sweeps warm air northwards and cold air southwards as it zigzags around the world. 6 miles above our head, it blows at hurricane force. Changes in the routes favored by the jet stream help, as we'll see, to alter the climate. Because at the Earth's surface, great eddies of air are related to the jet stream. They make the characteristic weather of the stormy zone in which we live.
In the stormy zone, a clockwise whirl in the winds marks an anticyclone and a spell of fair weather. Where the winds revolve the other way, it's a depression, where rising air makes clouds, like the clouds that a satellite sees in a depression that's nearing the British Isles. The storm is busily exchanging cold air for warm air. It's sweeping heat toward the Arctic. It all helps to ward off the next ice age, if you can look at it that way, when life is in danger at sea. But the price of warmth is too great for some. While human beings pay with their lives for the real weather, a mathematical model of this storm is raging in the circuits of a computer. It says the storm is shifting away. One storm is moving off, but there's usually another on its way. Weather news from all around the world provides raw material for the computer. Forecasts by computer aren't mysterious. To the weather information it received, the computer applies laws. About the air moved by heat, pressure, and the spinning of the Earth. About moist air turning to rain. The British Meteorological Office was the first to adopt the new generation of very powerful computers for routine forecasting. This display is the next step. It's intended to let experienced humans prompt the computer. A storm in the Atlantic, as visualized by the computer, doesn't seem to be intense enough. That's probably because too few observations have come in from the middle of the ocean. Another pressure line makes the storm deeper. The worldwide information is barely in before a forecast is due. The computer reckons the likely changes right across the northern hemisphere at 10 different levels in the air. It's a race against real events, so imitating the weather by numbers can only be approximate. 20 minutes figuring, that's all the computer's allowed to produce its predictions for tomorrow. And after doing 20 billion sums, the computer offers its forecast for the whole northern hemisphere for 3 days hence. There's more to come. So far, the computer has calculated at 3,000 points across the map. That means not many points on Western Europe, only about 50. Now the net's drawn tighter for the rainfall. More detail, more arithmetic. Forecasts of the weather high in the air usually go to the airlines untouched by human hand. For the weather on the ground, too, you don't alter the computer's forecast unless you have to. But human forecasters know the quirks of the weather, about the sorts of error the computer tends to make, and about small events like thunderstorms that the computer overlooks. The computer's more skillful, though, at grasping overall weather patterns. Together, man and computer have a partial comprehension, not always certain, of the daily weather. But it all depends on that worldwide information. When it's midnight Greenwich time, it's mid-morning in the Western Pacific. Beyond the ocean is a world that waits for news from the atoll of Truk. The weather observer's main tool is a little package of expendable instruments measuring pressure, temperature, and humidity as it rises in the air. It'll go up 20 miles. The same thing's happening in Africa. At noon and midnight Greenwich time, 700 balloons sample worldwide the weather of the upper air. As this balloon rises over Hong Kong, it carries a radar reflector. Tracking it reveals the winds blowing high overhead. World Weather Watch, they call it. Flyers report the weather en route. They know the value of reliable forecasts.
We estimate ACAP 47. Outside temperature -37 Charlie. Spot wind 230 diagonal 25.
And 7,000 merchant ships fill awkward gaps in the reports from mid-ocean. The pooled weather news flashes to every country, normally within 3 hours of the observations. It's routed through communication centers like the one in New Delhi. In free exchange for the weather reports, forecasts like this one made by the Indians' computer go electronically to any country that wants them. Nothing unites the nations like the war against bad weather. A cold front is edging out of China, but the news came well ahead of it. For nearly 20 years, despite the Cultural Revolution, despite wars in Asia, weathermen in Hong Kong have received meticulous balloon reports from China. They come in 4 times a day. And every day, from an American satellite, a gift of pictures. For 8 years now, anyone in the world has been able to receive automatic picture transmissions from our weather satellites. With a simple ground station, you just point your aerial to where the satellite's passing overhead. In this part of the world, the chief worry for weathermen is typhoons. Hong Kong is a small target on the China coast, but every few years a ferocious storm slams into the city. Refuge harbors are not a luxury. A modern radar gives precise details about an incoming typhoon. It need no longer surprise and kill, but the early warning comes from the satellite. The pictures cover 20 million square miles around Hong Kong. They're normal today. But they always check for anything that looks like the sinister spiral of a nearby typhoon.
Here's a model of a modern American weather satellite that broadcasts its pictures to anyone who wants them. There are strategic gaps in the World Weather Watch, especially in the tropics, the southern hemisphere, and the oceans generally. The hope is that satellites will fill in some of these blank spots. This one already carries infrared instruments that detect the Earth's heat rays. They tell the temperatures of the cloud tops and of the sea, and they even monitor the weather at night. This satellite orbits over the poles, and as the Earth rotates, it visits each part of the world once a day and once a night. But other satellites orbit in step with the spinning Earth and give non-stop observation of one huge area. The latest of that kind is called GOES, G-O-E-S. That stands for Geostationary Operational Environmental Satellite. It scans the light and heat rays from the Earth, building up pictures every half hour. Satellites are to the weathermen as the telescope was to the astronomers. They stand at the window of the weather machine looking in, and they show on nature's weather map what's happening over whole oceans and continents and encompass storms too wide for any ordinary eye. As satellites take their place alongside computers as powerful scientific tools, the meteorology of the 1970s can deal quite well with large-scale weather systems that develop over a few days. But the weather machine operates on many different time scales, from thousands of years for making or melting great ice sheets to the fleeting lives of individual clouds. To a large extent, clouds are the weather. So how well do the weathermen understand the clouds that show up fuzzily in the satellite pictures?
The United States, May 24, 1973. Between scattered clouds, Oklahoma bakes in the morning sun. Many farming communities, like Union City, population 300, lie scattered in a broad zone of North America where thunderstorms bring special dangers. Here, meteorologists shot unique film on that Thursday afternoon of what happens when colliding squalls set the base of a cloud spinning and seething. A tornado was born. It tore Union City apart in a matter of minutes. Astonishingly, perhaps, only 2 people were killed, but it caused $1 million worth of damage in this one small town. 1973 and 74 were America's worst years for tornadoes on record. And a tornado-chasing unit, armed with radars and cameras, watched as pieces of Union City were flung about like leaves. The deadly violence of these storms remains puzzling. To imitate the action of tornadoes, Ted Fujita runs a machine at the University of Chicago. Its revolving cups force the air to spin. Dry ice in water forms a fog to make the vortex visible, while suction through the hood draws the air upwards. A strong updraft and rotating air. By the usual theories, that's the recipe for making a tornado. Fortunately, it's not the whole story. Otherwise, tornadoes would be far commoner than they are. Apart from the obvious vortex, there's an invisible process going on even in the model tornado. The machine shows a curious effect. Put on too much suction, and the tornado collapses. Reduce the updraft again, and it recovers. So what really keeps a tornado going? It seems to be a current of air that comes downwards around the outside of the vortex. Block off that fast downdraft, and you kill the tornado. So let it flow again. Professor Fujita's theory is that sometimes a sudden unseen draft of cold air drops from the top of a rotating thundercloud. That may be what sets a real tornado going. Research into causes of tornadoes should make them more predictable. It's already helping save lives. The prime agents of the weather, the clouds, appear when moist air rises and cools. They lie between the level where the air becomes too cold to keep its water vapor and the bottom of the stratosphere, which is a kind of lid. In relatively warm air, water droplets make puffy clouds. In colder air higher up, ice crystals form, and the clouds are streaky. Most of the world's rain is melted snow. But first raindrops and then snowflakes can form only with the help of minute particles of dust in the air. For instance, salt spattered from the ocean, or dust from volcanoes, or even smoke from a car. Sometimes a cloud may contain water all ready to form more droplets or ice crystals, but which doesn't do so because it hasn't had enough of the right sort of natural dust. You can then try to encourage rain by seeding the cloud with special materials. The discovery that humans could really affect clouds was made by this American. Nearly 30 years ago, Vince Schaefer was in his laboratory making clouds. It was a hot day, so he grabbed some dry ice, frozen carbon dioxide, simply to help cool his freezer. But doing that transformed the cloud. Water droplets, already chilled, froze into sparkling crystals of ice. Even the smallest pieces of dry ice did the trick. Later, he dropped dry ice pellets into a cloud over Massachusetts and transformed it, the first successful seeding. Around the world today, dozens of rainmaking operations are in progress. How does the pioneer judge the possibilities?
Under the right conditions, it is quite feasible to get a 20% increase in the precipitation from a cloud system. And we have evidence now that hail and other severe storms can be modified. I think the time is rapidly approaching when we will be able to no longer depend on the vagaries of the weather, but perhaps can do something about it. It may be easier to control the weather than to forecast it.
But unless you can forecast how clouds would behave naturally, how can you be sure that you've really controlled them? Humpy cumulus clouds, like these over Florida, are prime targets for the hopeful modifiers of the weather. The U.S. government's environmental research laboratories have long-running trials in progress. Joanne Simpson and William Woodley are trying to settle a vexing issue. Can human beings, by seeding clouds, genuinely alter them to a worthwhile extent?
Can we turn back in here, or is it too close? How about a 270 to the left?
Okay.
Outside the aircraft are mounted the silver iodide flares that help ice to form in clouds. But they don't necessarily fire when the order's given. That's decided by drawing a card at random, saying whether to seed or not. Today, the card says seed, but the experimenters up in front, as they select their clouds, don't know that.
Okay, Fritz, you ready?
Ready?
Fire 1. Fire 2. Fire 3. Fire 4. Fire 5.
They must judge any growth that occurs in the cloud without knowing whether they've really seeded it or not. That's to avoid bias.
Fire 6. Fire 7. Fire 8. Fire 9. Fire 10.
Only thorough statistics will convince the skeptics that rainmaking really works. Stationed across the Florida farmland, rain gauges give some evidence of increased rainfall directly under the seeded clouds. But does the seeding really make more rain over the target area as a whole?
Okay.
After 37 days of experiments spread over 4 years, Dr. Simpson and Dr. Woodley still can't say one way or the other. They need another 60 days in the air. In any case, nothing that humans do can yet compare with nature's casual building of a thunderstorm over the mountains of New Mexico. We're seeing it speeded up 100 times. Human hopes for modifying the weather know no bounds.
Yeah, this heading ought to be...
Another flight and a considerably different mission. A rendezvous with a hurricane. Project Storm Fury aims at eventually moderating the mightiest storms on Earth. They're feeling their way towards the central eye of the hurricane. Hurricane Ellen makes no headlines of disaster. She's steaming safely northwards through the Atlantic near Bermuda. Nobody's going to interfere with Ellen today. They just want to learn more about her. Their approach to the eye is recorded on the radar. The eye itself is calm, although among the towering clouds around it, the wind blows its strongest.
Say, John, it's picked up. We got 45 knots now. John's did not be ever reading anything of it. I haven't seen...
The hurricane feeds on the ocean and stirs it deeply, so elaborate but expendable thermometers drop into the sea. They signal the temperature at different depths as they sink. On this flight, they disclosed underwater waves in the wake of Hurricane Ellen. And there was particularly good news for the would-be tamer of hurricanes. A battery of instruments measured the ice and water in the air. They revealed, even in cold air, a surprising amount of liquid water. So much water, just asking, as it were, to be seeded and turned into ice. Yet, how could man influence a storm which releases energy at a rate equal to a hydrogen bomb every minute? The only chance would be to touch some critical point where a small change might have large consequences. From far and wide across the ocean, a hurricane or typhoon or cyclone, call it what you will, sucks in moist air. It throws it skywards in a wall of clouds around the eye. The water it carries now freezes, releasing energy that powers the storm. But American hurricane experts suspected that the storm's clouds would still contain a lot of water overdue for freezing. Seed the clouds here with silver iodide to encourage ice to form, and you might spread the zone of high winds and weaken them. In 1969, they seeded Hurricane Debbie, and it did seem to weaken, but that could have been just a coincidence. In any case, one man's shipwreck is another man's harvest. You have to be a good climber to be a radar engineer here. But at least the slope is even. They're climbing Mount Fuji in Japan, making for the summit 12,000 feet high. They have to supply and maintain the most elevated weather radar in the world. Built here despite the cold and fierce winds, it's very awkward to keep manned and serviced. The Japan Meteorological Agency never regretted the effort. Patterns of rainfall detected by this instrument are copied to all parts of Japan. But the special value of this lofty vantage point is that the radar can pick up, even 500 miles away, the signature of an approaching typhoon. It gives the Japanese ample warning of where danger threatens and so saves lives. Japan suffers some 4 typhoons a year, $400 million worth of damage. Yet, typhoons are welcome here because they bring 1/4 of all Japan's rainfall. So, Japanese strategy is clear. On the very rim of Fuji's volcanic crater, they have the keystone of their defenses against typhoons, the early warning radar. Be vigilant, then let the storms do their worst, and rejoice in the rain they bring. With this outlook, the Japanese want no one monkeying around with their typhoons to spoil their farming climate or else make the storms worse.
So the Japanese are definitely not pleased that the United States and the Philippines are planning typhoon-busting experiments in the Pacific. The oceans, with storms raging over them and currents sweeping through them, play a decisive role in the world's weather. Like the air, the oceans are always on the move, but they're more difficult to study. It's only recently that ocean scientists found out that the oceans are full of tight little eddies, the watery equivalent of storms. Yet, what happens in the oceans has a major influence on the world's climate. Take the North Pacific in the 1960s. Then the surface water near Hawaii was rather cool. It was warm near the American coast. That guided the jet stream of the upper air along a path that brought warm weather to the western U.S., but left the eastern side of North America in the grip of cold winters. But that didn't last. In the 1970s, the sea temperature changed around. The jet stream has since tended to follow a different route, bringing cooler winters to California and warmer weather in the east. And urgent new research has begun into how the air and the sea affect each other in the Pacific Ocean north of Hawaii.
The ocean is the second great fluid of the weather machine. The water's massive memory for heat and cold lasts much longer than the air's. Shallow patches of warm or cold water influence the weather in the air above. But the weather alters the water, and an American expedition is equipped to study the interplay. The good ship Flip gropes 300 feet into the subsurface waters by upending itself. The gear aboard her adjusts itself to life on the perpendicular. Well, most of the gear. Flip now monitors any changes of the various depths as she drifts in the North Pacific. And for a simpler and cheaper way of doing it, they're testing a giant buoy, 40 feet wide and proof against typhoons. It has a nylon tail with instruments on it reaching 1,600 feet down into the water. It automatically transmits news of the temperatures of the different layers. Everyone's after the water temperatures. This aircraft is armed with those expendable thermometers that sink into the ocean and signal the temperatures. Strange to say, it's only now that meteorologists and ocean scientists are really joining forces to ask basic questions about the oceans and the world's weather. How deep do the surface patches of warm or cool water go? How do currents and eddies affect them? How readily can a storm change the sea temperatures? This trial confirmed fears that the water's own weather is intricate. Comprehension of the oceans will come neither easily nor quickly, and the weather within them can be calamitous. The sea off western South America is usually bountiful. In 1971, Peru gathered the world's largest fish catch from water teeming with anchovies. Then the water changed. By 1973, the fishery was wiped out. The fishermen wait for the anchovies to return. They call visitations of this kind the Christ child, El Niño. They usually happen around Christmas. In normal times, a strong current flowing from the south eases away from the coast near Peru. In the gap, fertile water wells up from the depths of the ocean. If the current shifts inshore, it blocks off the fertile water and fishes starve. But part of the portrait of El Niño has to be drawn 9,000 miles away across the Pacific. In the atoll of Truk in the Caroline Islands, you're a long way from anything except the ocean. The tropical water hereabouts issues huge amounts of heat and moisture to the air. The ocean itself, the wet part of the weather machine, rivals the air in carrying heat around the globe. The fisheries of these islands neither aim so high nor crash to disaster like those of Peru far away. But they're linked by the flow of the ocean. Between Truk and the nearby equator, a great eastbound current of water runs against the prevailing trade winds. It carries warm water towards South America at up to 40 million tons a second, but sometimes it almost stops. When it surges strongly, the sea level falls a little here. That's the simplest way to detect the current's fickle behavior. Dave Miller's line is really electronics, but he takes care of the sea level here to oblige the folks who like to know such things. Someone will have to interpret this chart to find any small change in mean sea level. The ordinary tides have far more effect than that erratic current does in dropping or lifting the float that drives the recorder. The records are highly prized in a more accessible part of the Pacific. Here, too, in Honolulu, the trade winds blow. Sea level changes at various islands speak of surges in the currents. Klaus Wirtke of the University of Hawaii connects them with El Nino, which ruined the fishermen of Peru.
El Nino coincides with the surge of the currents in the mid-Pacific. The current transports vast amounts of water, of warm water, into the eastern Pacific Ocean, from where, for the months to come, it may affect the climate, for instance, of North America. There are a number of visitors around here, and I wonder whether these visitors realize that the weather at home in the months to come will be affected and created by the events here in the mid-Pacific. I think the surge in the current explains El Nino. Some of my colleagues disagree. They say weaker trade winds are causing El Nino. Now, my current runs precisely against the trade winds, so weaker winds will cause a stronger current. But what, in turn, makes the trade winds weaker? The ocean currents or the warm ocean surface water? You see, this is the kind of circular argument that we are getting into when we try to fit the pieces of the weather machine together all over the world.
The weather off the Pacific eventually arrives in California. And here to receive it is Jerome Namias of the Scripps Institution of Oceanography. For years, he's been studying the sea temperatures that are measured by merchant ships going about the world.
The ocean can affect the atmosphere over enormous distances and in fairly predictable ways. Take the weather today, for example. We're now on a beautiful day, bathers along the beaches, but actually we're sandwiched in between two storms. This is related to some very cold water, perhaps 600 miles off the coast, while farther to the west there's a warm pool of water, and the difference in temperature between these currents is causing these storms to move southward, affecting us right here. Now let me give you an example how the sea surface temperature patterns can influence all our lives.
In the Atlantic in 1972, patches of very cold water and warm water lay close together. The jet stream of the upper air became locked between them. It guided cold weather to Britain, which had a dismal summer, but it left the Russian grain lands with a great drought. World prices of grain shot up. Meanwhile, there was a trough of low pressure over the eastern United States. Hurricane Agnes was drawn into it, causing the worst floods in American history.
That's only one case, but we've all lived through spells of abnormal weather, including droughts, floods, hurricanes, and so on. And in order to forecast these things correctly, it'll be necessary to take into account the temperatures of the sea, not only locally, but over far reaches of the whole planet.
Long-range forecasting using nature's symptoms is gradually improving. Other problems surround the short-term predictions. Today's official forecast for this island in the Pacific was, you guessed it, sunny and dry. It's a freak rainstorm, too small and too short-lived to be predictable, and far beneath the notice of any computer. Yet these small events directly affect human life, and they also have hidden influences on the development of larger weather systems. So, small storms are not just awkward to predict in their own right, they also sap the power of the computers and undermine present attempts to predict the wider weather for a week or more ahead. The computers calculate at a limited number of points. They cope well with such a big depression, but not so well with small local storms. The small storms also slip undetected through the network of global observing stations, so the world's weathermen don't even know they exist. Not normally, anyway. Inexact starting information can send a computer forecast astray. At the U.S. National Center for Atmospheric Research, Cecil Leith wrestles with this element of chance.
The forecast is pretty much of a gamble. We have to learn how to hedge our bets. I'm using what is called the Monte Carlo method. Starting with the weather conditions on a particular day, we make a series of two-day forecasts differing by small amounts corresponding to our uncertainty in the initial conditions, and examine the development in each of these 8. We note, for example, that over China, a low moved toward the coast. In all of the 8 forecasts, we can be quite confident that this will happen. We also note another low near the Baltic, which remains stationary over this 2-day period, according to these 8 forecasts, and we can be confident of that. However, over the North American continent, the 8 forecasts showed quite different behavior, and in this case, we would have far less confidence in the validity of our 2-day forecast. Our best bet is the mean of the 8 forecasts, and in fact, as we compare that with what actually happened, we see reasonably good agreement for the lows in the Baltic and Asia, but some disagreement over North America. It is through a technique such as this that we hope that we'll be able to understand better how much confidence we can place in a forecast of, let's say, a week in advance.
Faster computers and better weather reports might cure half the errors in routine forecasts. But for a real breakthrough, more basic knowledge is needed. Okinawa has a doleful name. In 1945, this Japanese island shook with battle. In the end, the chief defender threw himself off this cliff. Today, only fishing boats litter the once disputed beaches, and Okinawa's the first theater in a quite different war. Each February, a bitter wind breaks out from China. As the islanders take in their sugar crop, they expect rain. The ocean is always warm in these parts, and it transforms the cold wind into a milder and wetter mass of air. The weathermen have made Okinawa their headquarters for the air mass transformation experiment. It's the first big operation in mankind's global atmospheric research program, aiming at better understanding of the processes of the weather. American satellite pictures assist them, and their research in turn will help forecasters all around the world. China influences the winter weather of the nearby ocean. The area is bathed by a strong warm current from the tropics. On convenient islands and specially stationed ships, the experimenters watch what happens when the cold, dry wind from China reacts with the sea 40 degrees warmer. It takes up moisture like a sponge. From the sea, invisible fingers of rising air carry off cargoes of moisture, fuel for the weather. The flows of warm air and moisture reveal themselves to towers festooned with sensors. It's all in aid of a quite small part of the weather machine, but one which affects the climate all around the world. Some of the instruments are very simple. This windmill measures the lift of the air. Others are ingenious, like the one that uses sound waves to feel the air moving through it in any direction. The effort is mainly Japanese, but weathermen from America and Australia have joined in. It seems fitting to take the measure of this Chinese wind with a kite. The instruments it carries measure the condition of the air at selected heights. The rising moisture gradually turns into clouds and rain. Meteorology has come a long way since the days of the old weather glass. A radar picks up potential raindrops beginning to descend a mile overhead. Some of the moisture that the sea surrendered to the air is already on its way back to it. The experimenters find that more than 4 times as much energy passes from ocean to atmosphere when the cold wind blows as does on a warm day. The facts and figures will let the world's computers put more accurate numbers to an atmosphere that boils and swirls whenever a warm sea is swept by a cold wind. The Japanese experiment off Okinawa will continue, but there'll also be a big study by the Indians and Russians of the monsoons of southern Asia. To fill in another gap, special weather buoys are going into the lonely Southern Ocean. And the Japanese, the Russians, the Europeans, and the Americans will also station satellites at agreed intervals. Together, they'll give continuous weather observations all around the world.
The new powers that their satellites and computers give them have spurred the world's weathermen to a massive attack on the problems that still vex them. For another example, the Americans and the Russians are planning to see how Arctic ice affects the weather. They'll be using manned icebergs. It's all leading up to a global experiment around 1978. One aim of the Global Atmospheric Research Program, as it's called, is better weather forecasts for a week or more ahead. Now, there's increasing stress on a second objective, to understand changes of climate before they hit us any harder. Already in 1974, an extraordinary effort has gone into seeing more exactly how the clusters of clouds over the tropical oceans power the whole world's weather.
The northern hemisphere, mapped by satellite, has a necklace of cloud clusters strung all around the equator and pumping vast energy into the weather machine. In 1974, the Americans stationed their newest weather satellite, called GOES, over the tropical Atlantic in time for the big party. In the late summer, the fashionable place for a weatherman to be was at Dakar in West Africa. A huge research armada assembled for the biggest international experiment in the history of science. The Atlantic Tropical Experiment of the Global Atmospheric Research Program, GATE for short. The Russians are here in force, and the Canadians have pulled their finest weather ship off station. Altogether, 40 ships from 10 nations are taking part. The world's nations are investing $300 million in the experiment. At Dakar Airport, Russian and French, British, and American research aircraft await their orders. Dakar is in Senegal, one of the African states hit by the recent drought. Near the coast, the people still prosper because there's fish to be had. But inland, those driven from their lands by lack of rain live as best they can. The governments concerned like to think the GATE experiment will help them judge better the prospects for their people. Under the UN flag at Dakar, the leading organizers of GATE include John Mason, head of Britain's Meteorological Office, and Joachim Kuttner from the USA. Pictures from the GOES satellite show the weather offshore.
So some of these aircraft missions then will be 10 or 12
Dr.
hours.
Kuttner's in command of the daily operations, and he has a welcome target. A cloud cluster is approaching the main experimental area, and it's to study how and why nature forms these ordinary yet vital clouds that researchers put to sea, bound for their appointed stations. Working to a strict timetable, the scattered fleet records the weather high overhead. We're aboard the Professor Zubov from Leningrad. Concentrated effort for a few months should reveal general rules on which the computers can rely ever after. Subtle mechanisms, both high in the air and deep in the ocean, may help to determine when cloud clusters will develop. Temperatures and saltiness at different depths are measured from the Canadian weather ship Quadra. A Christmas tree of instruments will register the upsurge of heat and moisture from the sea, while Quadra's powerful radar probes the clouds that form over the surrounding ocean. They'll signal the radar picture to the headquarters ashore. It's a valuable guide for the airborne missions into the weather that's unfolding over the tropical Atlantic. Such elaborate international efforts for studying the life of commonplace clouds marked mankind's impatience to know the weather machine better. Vast numbers of clouds, big and small, graze together on the warm ocean. From the satellite, a day in the life of one cloud cluster just off the coast of Africa.
GATE, This experiment in the tropical Atlantic sums up the character and hopes of modern weather research. And because atmospheric waves going all around the world help to conjure up cloud clusters in the Atlantic, countries from East Africa around to South America have been supplying weather reports for GATE. As the satellites look down on the area, the computers calculate what the winds are doing. International collaboration is driven to the limit. The core of the experiment is here, a trap for cloud clusters made by 20 ships, Russian, British, Canadian, French, German, and American. They caught their cloud clusters. For instance, on the 30th of August, this one was pumping busily away over the core area, and the aircraft from Dakar went in to patrol among the stormy clouds. The experiment seeks general interactions between the cloud clusters and the global weather. Some cloud clusters turn into hurricanes. Here's one just forming that hit Louisiana, and here's another that's moving right into the weather of the North Atlantic. The main hope that inspires this very difficult research is that computers will predict the weather more reliably and further ahead. But meanwhile, to understand seasonal trends, the weathermen, as we saw, have to read all the available symptoms and take the temperature of the sea. In July of 1974, cold water on either side of North America conspired with the jet stream of the upper air to leave the American Corn Belt in drought. But by August, the route had changed. Letting cold polar air caused disastrous early frosts in Canada. Held south of its normal track by a cold Atlantic, the jet stream gave northwest Europe, too, a cold summer. And in early September, it guided unseasonable storms into Europe. On this particular day, the GATE experimenters observed another cloud cluster forming off Africa. It traveled west, and sweeping energy up from the Caribbean, it evolved into Hurricane Fifi, which flooded Honduras in one of the worst disasters of the year. In passing, Fifi robbed the world of a large crop of bananas, and the direct human suffering was terrible. While thousands drowned in water and mud, many others had narrow escapes. Every one of us is in the front line in mankind's endless war with bad weather. Fifi was only a skirmish. The weather machine is capable of far worse harm even than this. As it threatens the world with drought and cold, other ways of investigating the climate become important. The ice samples from the Greenland drillings informed us about weather of past centuries. We're going to see how pieces of living trees, the mud of the oceans, and the pollen of plants long since dead warn us about what our planet may have in store for us. And we'll hear of startling new discoveries about the risk of another ice age. But first we have a short intermission. I'll be back in a minute.
This program is being made possible by a grant from Champion International Corporation.